Am I audible, sir? Shall I proceed?
Yes, sir, you are audible, sir.
That's nice. Can you see the first slide?
Yes, sir, we are can able to see, sir.
Okay. Good evening, the organizers. I thank the organizers for giving me an opportunity to present a talk in this AICT ATL sponsored program, faculty development program. My topic of today's talk is high performance materials for sustainable nuclear technology, challenges and opportunities. So my contents of presentation will be of as follows. I'll have a brief introduction about what is tribology, what is the background of nuclear technology, what is the significance and usage of high performance materials, what are the types of high performance materials, what are the challenges faced in the material development, what are the opportunities for improvement, and I present my case studies to this gathering. What could be the future directions, policy and regulatory conditions, summary and conclusions, need of the hour, and you can the final one is contact information about for future clarifications. So, introducing about sustainable nuclear technology, the facts about nuclear energy. Nuclear fuel is extremely energy dense. This picture gives you a clear-cut view about how does a 1-inch tall uranium pellet is capable or is equivalent to 17,000 cubic feet of natural gas, 120 gallons of oil, and 1 ton of coal. So then the question arises in our mind is nuclear energy sustainable? So we have several demonstrations, several outreach programs, especially for school students, especially for college goers and the public, to create an awareness about the sustainability probableness of nuclear energy, the sustainability possibleness of nuclear energy. So when you have the concept of sustainability, you can see how amount of carbon dioxide pumped in the event of producing a power. So in terms of carbon footprints, nuclear energy is highly sustainable. Uh, this picture gives you a clear-cut idea how does a 1-inch tall of uranium is equivalent of how much amount of natural gas, oil, and the ton of coal. So when you speak about any sustainable ones, we need to go with some facts. We should understand about the sustainability of nuclear energy is all about the three important dimensions. One is on the environmental perspective, which we should have a lesser amount of carbon footprints. We should not spoil by having polluting the soil, polluting the water, or polluting any of the air atmospheres. The other one is the economic dimensions, the viability of producing the power per watt, the cost involved in producing the per unit consumption. It should be economical, it should not be more. And the social dimension, how it is people friendly, how it could be human friendly. So in these three dimensions, all the sustainable technologies work on. When you closely have an introspection into this sustainability of nuclear energy, it has its economics, infrastructure, proliferation resistance, safety, waste management, and environment. So the nuclear energy is committed as we have sustainable development goals. You can see the goals gradually coming up from the good health, well-being. It could be affordable and clean energy, decent work on economic growth. It's being projected for the 2030. It have been 17 goals to eradicate the poverty, and it will guarantee the prosperity for all through the committed sustainable development goals. It can address the industry innovation and infrastructure. It will become responsible for the consumption and production. And the final one is the climate action. Nuclear energy helps to mitigate the climate change which is being produced large quantities of electricity without carbon dioxide emissions. So in nuclear, we use the chemical fuels like uranium oxides, uranium carbides. So there is the amount of carbon dioxide produced from the fossil fuel is tremendously more when you use a conventional thermal power plant or an oil gas powered naphtha based power plants. The CO2 emissions are incredibly more when you compare head on with the nuclear power plant. So this is the head-on comparisons and the current existing stations around across the nation. So when you see the amount of power being produced in the global perspective, you can see the major person who is playing a vital role in the nuclear power share is United States. Next comes gradually you have Chinese and the France are on the second and third respectively. Simultaneously, when you gradually get into that, our contribution is much lesser in this. You can see just 1.6 percentage we are contributing to the global nuclear power pie chart ratios. Whereas when you see out and out, what is the location of our reactors across the nation, you can see how much amount of in Rajasthan alone we have 6 plants, namely RAPS 1, 2, 3, 4, 5. RAPS is nothing but Rajasthan Atomic Power Plants. And then Uttar Pradesh, we have 2 plants, NAPS 1 and 2, Narora Atomic Power Plants. Kakrapar in Gujarat, we have 1 and 2, CAPS 1 and 2. In Tarapur, we have 1, 2, 3, 4, 4 plants in Boisar, Maharashtra. In Karnataka, you have Keiga stations, namely KGS 1, KGS 2, KGS 3, KGS 4. You have 4 stations. In Madras Atomic Power Plant, you have 1 and 2. The latest addition to our country, Kudangulam Power Station, KKNPS 1 and 2, 3 and 4 are under construction. So these are all the geographical locations of nuclear power plants, most of them located very proximal to the seashore or some of the places where desert. So geological thorough survey is being carried out before installing the power plants. So when you have look into the advantages of nuclear technology, you may immediately think about why don't we go for a renewable like a wind energy or solar energy. The main problem in addressing your peak loads cannot be addressed by renewable energies because wind is not available throughout the 12 months in a year. Like this month, current month of September, August, Adi, Avani, these 3 months only you get good amount of wind. After that, it's very seasonal. And one more thing, when you depend on solar, you cannot address the peak loads during nighttime conditions. So high power output throughout the production is possible only in nuclear power. Then the second one is nuclear power is a clean energy source because the amount of carbon emission to the environment against 1 kilowatt production is tremendously low compared to the fossil fuel productions. Then it is highly reliable because you should understand about how to have a head-on comparison between a nuclear reactor and a nuclear bomb. Both works on the principle of nuclear fission, in which you have uncontrolled reactions, in which enormous heat is produced. But the basic difference in a bomb is the reaction is totally uncontrolled. The heat is proliferated just like that. Whereas in nuclear reactors, we have structures called control rods, boron carbide rods, which will act as a neutron poison. We can immediately come to a shutdown of by cutting down the neutron supplies, and the nuclear reactor can be gradually, it could be coming to a standstill. We can go to a stop conditions by using stopping of the nuclear reactions by cutting down the supply of neutrons. Neutrons will be absorbed or poisoned using the neutron absorbing control rods. So that kind of reliability gives you a major reason to depend upon the nuclear reactors. Then you have almost zero carbon emissions because the coal or any fossil fuel involved in this production is nil. So we proudly say it has zero carbon emission. And compared to the rest of all power plants, it has low operating power cost. Then you gradually get into the second topic of my presentation, that is background of nuclear technology. When it evolved from 1945, it started evolving, and till 2020 we have the data. From 1945, though it has been started as a bad initiative for nuclear weapons from America, Russia, UK, and France, gradually it goes into several histories of incidences in the calendars. When you see about a few of the mishaps, it was like everyone speak about the Chernobyl accident, the 3 Mile Island, Fukushima accident. So we have been continuously learning those mishaps, like Fukushima accident due to the earthquake and the flushing of the seawater inside. Our own nuclear reactors in Kalpakkam, we have raised the height of the DG backup 17 meters, above 17 meters, taking the account of last 100 years of tsunamis, the maximum height of the tsunami wave. We have almost doubled the size of the wave in order to establish safety and ensure the safety of the not just the nuclear power plant, also the surrounding villages. So what is this purpose of this particular presentation? I just want to educate the audience. I just want to highlight the challenges, explore the opportunities, showcase real world applications, encourage future research, inform the policy and decision making involved in nuclear reactor, engage and inform the stakeholders, and summarize the key points. So what is the generations of nuclear power plants, nuclear reactors world has witnessed? You can see generation 1 reactors, generation 2 reactors, generation 3 and 3 plus, and generation 4 reactors. We are gradually, you can, if you closely understand the first prototypes and the commercial production of the electricity, then you have the advanced and evaluative reactors, and the final one is the innovative devices, innovative designs. So in the innovative designs, we are frequently looking to the concept of sodium cooled fast reactor, and current days SMRs have come, small modular reactors, then gas cooled fast reactors. In UK, they have fusion-based reactors. ITER, they are working on the global. If fusion is possible, the entire globe can get the power from one particular reactor. ITER is one particular such reactions. This can do is one which in maps we have it. This is our current condition, third stage reactors in this. So this is the particular generation of reactors what we are going to evolve from that to the current sodium-based PFBR reactor. We are just about to commission in a few months from now. So this particular slide gives you about the evolution of the generation from 1 to 2, 3 to 3 plus, and 3 and the fourth one. So this could be the next roadmap of the nuclear reactors evolution in terms of power plant designs. So if you see about the brief overview of the technologies and the dynamic developments, you can see how does this concepts are. You have the science of publications. What is the impact created in that? What amount of modeling it is being including? What amount of publications are being there? How much amount of patents have gone? So due to the patenting, what is the impact on the economic growth? How does the product commodity has an impact on the economy? So then we go after the conceptualization, when you go to the methods involved with that. How does nuclear power uses Bayesian model, systems modeling, and these are all the other sources where we have collected the data. Then how does these findings will have impact in the future evolutions and the historical tracks? So the current state of applications in nuclear technology, you can see the demonstration of a first reactor, which is of lesser than 10 megawatt micro reactors. That is then gradually adapted to the commercial micro reactors, because the days from 2021 to 2030, we are emphasizing more on small modular reactors. The micro reactors, the SMR operating by 2026. From there onwards, versatile test reactors and non-LPWR advanced demonstration reactor by 2030. This will be the roadmap. So though we are looking to the current one, this is the so-called three-stage nuclear program what our India is totally emphasizing. This is totally different from the power program which America follows. Here we have the used reactants will go as the input for this stage, and the used fuel will go as reactants to this stage. And already we have enormous availability, around 800 billion metric tons of thorium in our seashore. If we want to use those thorium, we should successfully commission the second stage. Then this second stage will make use of this thorium-based resource, which is available in our abundant in our seashores. So this cycle makes us to understand that our waste what we generate is going as the input for the next reactor, and the amount of waste what we are generating is very minimal, which will be stored in the underground repositories or it would be recycled in the form of waste mobilization projects. It will be made into glasses, which is silica, which is of higher stability. This is the way. We are not going to dump it on sea. We are not going to have a poor waste management. So the waste management of the nuclear reactor program in the Indian subcontinent is actually a very safe as well as a closed loop, where the exiting reactants and the products goes as the input for the next stage of reactors. So if you see this, you'll understand what is this is actually the submarine which is coming out of it. That is actually, when someone says it's a nuclear submarine, we all believe that the submarine is capable of bombing nuclear bombs. Actually, that is not the case. The submarine propels, gets into the sea and stays below the sea. So for propelling it to the depth of the seas, you need a power. For that, the nuclear energy is used. India's new nuclear submarines, INS Arihant, which is officially commissioned by our minister, which has got naval capabilities. The strategic importance of this one is actually the INS Arigat enhances the strategic deterrence capabilities. Somebody is trying to deter. It has a good deterrence capabilities, further strengthening the position of underwater security, especially using the nuclear deterrence. And overall, defense posture is very well sustained. So if you see a close view of a ballistic missile submarine, these are all the uh, components which is being stored. From the nose, it has torpedoes. Then you have pressurized hull. Then the crew quarters. You have the crew quarters where the people who stay inside. Once they get into the submarines, they normally go by number of days, ranging from 2 days to 40 days, 48 days. They stay inside the seawater and they keep sensing the radar signals and they keep on sending the data about what is the current condition, what is the wave currents, how does it exist. These kind of values will be coming out. And it has a propulsive ballistic missile. From the ballistic missile, it goes to the deep and it stays there. So you can see how does this ballistic missile tubes are placed right just behind the crew cabin. Then you have the nuclear reactor room. Finally, you have the turbine and the engine room, the propeller, which makes it to propel downwards in the deep seas. That part of my talk is importance of high performance materials, which is being used in the reactors like GCR, gas cooled reactors. So in gas cooled reactors, the coolant what is used is helium. The stability at high temperature, there is no limit for the temperature. It is going beyond particular thousands of degrees. So we need to have a material which will withstand thousands of degrees of Celsius. So the ceramic fuel coating becomes unavoidable to retain the radioactive material at 1600 degrees Celsius. We all know graphite, which is an allotrope of carbon, due to its high temperature resistance. We personally know graphite is mostly used in the lubrication of some kind of hot forging involving steel tubes. The temperature limit in which the graphite can withstand is actually 2500 degrees Celsius. You can see the uh, uh, assembly view of a particular fuel compact and fuel assembly of a gas cooled reactor, in which you can see the strategic importance of materials like silicon carbide, which gives you the high density. Then you have the fuel kernels, low density POIC, and you can see size of the fuel pellet. Fuel compact is 2.6 centimeter by 3.9 centimeters. You can see the fuel assembly, which is a very, very smaller size, 36 centimeter by 58 centimeters. So this one gives you the idea about significance of important materials used in gas cooled reactor. So as we saw the three-stage nuclear reactor program of India, you can see how does the PHWR, which is a first stage nuclear program, uses the natural uranium, produces 12 gigawatt electric energy. Whenever the power is being stated, you please concentrate on the suffix, whether it is thermal energy or electrical energy. When you have a suffix of E, it is gigawatt electrical energy. You can see the producing power time is 30 years. The pressurized heavy water reactor, supplies you the depleted uranium and plutonium, which in turn is further fueling the second stage nuclear reactor, which is called the fast breeder reactor. So the name change from PHWR to FBTR or fast breeder reactor is the neutron which involves in making the fission in PHWR is thermal neutrons or slow neutrons, whereas the neutrons which are involved in the chain reaction of this stage reactors is called fast breeder, fast neutrons, giving the reason for the names of fast breeders. Here we, in this point, we are using the environmentally available thorium as a blanket. Once the second stage is fully functional, here you have the production of the PU fuel fast breeders with the blanketing of thorium. It will create. Currently, we are in the second stage. From the blanketing of the thorium, you get uranium 233, which is very, very vital to fuel this naturally available thorium in our beaches. So the U33, which is generated from the second stage reactor, the current expected or the amount which is going to be produced is 300 gigawatts, which is about for 30 years. Imagine we have successfully crossed this in a couple of months time to year end. If we can complete this successfully immediately, this third stage could be on process, which can give you abundance of energy. The energy is rated as, you can see, about 500 gigawatt. It can be providing a life of 500 years. It is being calculated exponentially with the amount of available thorium ore in our beaches. So these one, two, three are the three stages, and second stage is actually our Bhavini, Bharatiya Nabikiya Vidyut Nigam Limited has commenced activities on the second stage. It is going to get commissioned very soon. So if you see, this is the existing prototype fast breeder reactor, which is first of its kind nuclear reactor in the country. It has very important, prestigious project, the advanced construction stage. Then what is the fuel involved in the PFBR? You can see it's a mixed oxide fuel. Why they call it as mixed oxide? There are two kinds of oxides. One is plutonium oxide, another one is uranium oxide. The thermal power which is produced, which is expected to produce 1,250 megawatt thermal. When you convert that megawatt thermal into megawatt electrical, you get an electrical output of 500 megawatts. What is the coolant? The coolant is liquid sodium. What is the expected thermal efficiency? That is 40%. So this is a picture which I would like to share very recently. Our Prime Minister visited in Kalpakkam. So this is our previous CMD. He is explaining the working of the PFBR to our Prime Minister. So the main attraction in his visit was commencement of core loading. So the fuel core loading was witnessed by our Prime Minister. The significance of his visit is India's first indigenous fast breeder reactor. And upon the completion of the core loading, the fuel is being loaded. The first approach for criticality will be achieved very shortly. We are now facing some technical snags in the fuel transfers. We are looking on it successfully. Once it is mitigated, the spirit of Atmanirbhar Bharat, PFBR is indigenously designed and constructed in Bhavini, using the contribution of 200 Indian industries like MTAR, Larsen Toubro, Gammon, lot of industrial companies, not just government, but also private participation in the fabrication. Lot of companies have indigenously contributed. India's nuclear programs aim to meet the twin goals of energy security and sustainable development. Why we call it as twin goals? It not just eyes the energy security, but also the sustainable development. This is actually for the vessel head high quality. What are the materials used in the nuclear reactors? You need to have a high quality low alloy steel. Low alloy in the sense the elements which is alloyed will be a very, very narrow band of uh, tolerances. That makes the material to have desired mechanical properties. Then the reactor pressure which is expected to have a high quality low alloy steel. Then the control rods, obviously we all know boron carbide B4C is used as poison for neutrons. In few of the specialized nuclear reactors, you have silver indium cadmium alloy AgINCD are used as neutron poisoning or neutron absorbing. Reactor internals, which is of subassemblies, fuels, it requires a high quality stainless steel. You can see zirconium alloy and uranium oxide and inconel are to be the fuels in certain specific strategic reactors. So here we should understand about what is 316 and 316L stainless steels. Both are austenitic stainless steel. The gradual evolution from 316 to 316L and 316 contains little more carbon, whereas L contains, L stands for lesser carbon. This one 316 has liable to weld decay, it has weld issues, whereas for avoiding the weld corrosion, you have lesser amount of carbon, effective for acidic environments. L316L is not just high temperature, it can also for high corrosion resistance property is there in 316L. So when you see this particular image, you can understand what is the need of L or what is the need of chromium. So in that, we cannot avoid explaining what is sensitization, what is CR23C6 intermetallics. The sensitized zones, the chromiums get depleted from the grains and it goes and segregates on the boundaries. What happens when the boundary is getting sensitized? The requirement of the corrosion resistance properties in the grain particle is compromised and the chromium depletes in the grain and enriches the grain boundaries. So the enriching of the grain boundaries make the difference in the strength between the grain and the grain boundaries, which may cause a kind of corrosion, which will cause a stress corrosion cracking or otherwise intergranular stress corrosion crackings. You can see how does those intergranular in the grains due to the boundary corrosions which is formed by M23C6 due to the depleted chromiums go and accumulate on the boundaries, making the grains weaker. So this is the significance of amount of chromium in the 316. Then how do we classify the stainless steels? Depending upon the phase, depending upon the chemical compositions, we classify the stainless steels as ferritic stainless steels, martensitic stainless steels, austenitic stainless steel, precipitation hardening stainless steels, duplex stainless steels. Gradually getting to the fourth topic of the talk now. Types of high performance materials, especially in reactor materials. The reactor materials, high performance materials, what we are expecting is fuel materials, moderator materials, coolant materials, structural materials, control materials, shielding materials, advanced and emerging materials. So what is nuclear shielding? We need to protect the zone where the nuclear reaction is taking place. It should not have any exposure to human being. You can see the gradual layer by layer and what is the penetrating power. When you have a paper, you have almost all the particles getting passed through it except the alpha particle. The paper is not safe for a beta particle, gamma particle or neutrons. Only alpha particle is stopped by the paper. You go to the next level of shielding by a thin metal. It can shield the beta particle but not the gamma and neutrons. Both are very, very strong. When you get into the lead steel, which is a very, very known shielding material, it can stop the gamma X-rays. And when you have a particular polyester, which is going to be a shielding material for our future, that is water extended polyester material, that could also be capable of stopping the neutron. This particular material, a polyester material, which is now being in research for stopping the penetration of neutrons because they are very, very powerful. So then we see about how does the high performance materials are needed in the annular fuel rods. Whenever you have circular tube which is covered by another circular which has a hollow tube, we call it as annulus or annular. And the coolant has to pass just followed or the peripheral zones of the fuel tube. Internally and externally in light water reactor, the fuel rod has to be cooled. The coolant normally has to pass through it. The annular design increases the cooled surface area and reduces the conduction thickness. So we all know it is created by the vibration of the mechanical particle of uranium oxide. The dimensions are, you can see the dimensions of the uranium particles are ranging from 500 micron diameter to replace the solid pellets. So it is achieved by 82 percentage TD, increased density by 87.5 percentage, including 15 percentage of uranium metal powder in some samples. So this is actually the fuel rods which is being used. So high performance fuel materials. Now comes the ceramic silicon carbide cladding, which could replace the current existing zirconium alloy fuel cladding. So it has got a duplex design. It has two layers. And the silicon carbide has a favorable physical properties which compared to zirconium, which has lower neutron absorption, because the more the neutron is absorbed, the fuel reaction is getting compromised. So there is no creep deformation. Creep is all we all know due to the continuous exposure in a temperature stressed environment. The kind of stress in influenced or experienced in the materials creep. It can withstand high temperatures, chemically inert. It should not have reaction with some of the fuel. It should have higher strength, higher resistance, and radiation damage. So this was a cross-shaped design which has been proposed so that we can have more cross-sectional area. So now we gradually get into the challenges faced in the material development. We have basically three types of reactors which is being tabulated here. The inherent physical features of fuel, thermal conductivity, diffusion rates of gaseous species, and chemical compatibility of the fuel and cladding in turn determine the performance of the fuel system. When you compare these three systems, which is a pressurized water reactor, boiling water reactor, or pressurized heavy water reactor, you can see the types of fuel being used almost same in the uranium oxide, whereas just the enrichment varies 3% in PWR and 2% in PWR. PHWR is the one in currently we have in maps which use just natural uranium oxide. The coolant and everything is almost same. When you have the cladding material, you can see the various cladding materials which is being used of zircaloy 2 to zircaloy 4. In PWR, there is a one more additional clad material, zirconium niobium alloy. The overall operating temperature of PWR is maximum 325 degrees Celsius. Rest of them are both are less than 300 degrees Celsius. The operating pressure by itself, the name pressurized water reactor makes it to understand it works on 15 megapascal, where the rest is around 7 to 10 megapascals. The average burn up due to the higher pressure and higher temperature, we all understand why does PWRs are very much glorified because of the burn ups. What is burn up? What amount of megawatt per day you get in burning 1 ton of the uranium. This is how you understand the average burn up by the unit given here. What amount of megawatt per day in a day you get by burning 1 ton of uranium. In 1 ton of that is 1000 kg of uranium you burn, and you successfully get 50,000 megawatt. So whereas compared to the boiler water reactor, it is shorter by 20,000, and PHWR is which is very primitive and starting time reactors, that is 7,000 megawatts per day. Related power rating capacity, you can see it can create an 1000 VVERs. Here 200 VVR is in Kudankulam, TAPS is Tarapur, Rajasthan, 220 and 540. This is in MAPS, Kalpakkam. So the opportunities and improvement in nuclear reactor materials, the radiation resistance, the material should have the reactor material should have the withstand the intense radiation fields, developing materials with improved radiation resistance, corrosion resistance, which should have high temperatures and reactive environments can lead to corrosion, advancement in corrosion, thermal conductivity. The better thermal conductivity is expected for better heat management, and the efficiency with higher thermal conductivity can lead better performance and safety. Then the high temperature performance. The advanced alloys, developing high temperature alloys, which involve ceramics, becomes unavoidable because it can effectively operate temperatures above 600 degrees Celsius, particularly valuable for next generation reactors. And finally, the high advanced composite materials. You should understand composite materials. We have combined metals with ceramics, polymers that could offer superior strength and thermal properties. Then comes the advanced fuel materials, improving the efficiency of fuel materials such as going through more stable and high density fuels can increase the reactor efficiency with reducing the waste. Burnable poisons can absorb neutrons to control reactivity. Manufacturing and fabricating techniques, especially like 3D printing, additive manufacturing, create complex reactor components with precise material properties. Nanotechnology is also a vital, playing a vital role in the technology in terms of creating strength, toughness, and radiation resistance. This is about the waste management and reprocessing. Very important. The spent fuel has to be processed in developing materials for better handling. We have a technology called pyro reprocessing, in which the used fuels will be chopped, dissolved in nitric acid. It's a typical reprocessing of our MAPS fuel. Those containment should have materials for waste storages containers to ensure long-term containment to minimize leakage risks. Then you have the boron containing materials, which is meant for neutron absorption moderation, which is improved boron containing components for control rods and neutron shields. Graphites and other moderators are also used as better moderators. So first now I'm going to have a smaller case study of this is a classic example. How do we achieve the through thickness hardness of a LRP ball? Normally ball bearings we see about 10 mm, 5 mm. This one gives you an idea of making a larger diameter ball. Is the diameter of ball what we have to make the core hardness of 55 HRG is the diameter of ball. Imagine it is 93.5 mm, almost 10 centimeter size of a ball, almost like a shot put ball. So those balls we have the problem of having a particular core hardness weakness. The core hardness has to be there. You may understand what is an LRP. So large diameter balls in the reactor, we have to operate the fuel sub-assemblies from the top of the reactor's plate. In the top shield plate, we have to operate the LRP balls for locating the sub-assemblies in one place to other place. Gradually, after the fuel is burnt, the used fuel sub-assemblies has to go to the peripheries and the unused fresh ones has to come to the core. This has to be taken care by the LRP structure. So LRP will be moving to that particular locations only through the LRP balls. Now you may understand what is the significance of that large diameter balls. So what is the background of this particular patent? We have to have see about what is large bearing balls. How does the material matter? Because this ASEM 52100 is a medium carbon steel, which has got very minimal heat treatment zones. So we did a lot of background in this patent. We did critical, it has limitations because the limited case depth is only 10 to 15. So specialty steels are considered essential for making such balls. So they are used to be a technology called hardening through depths. And the invention facilitates the substitution of expensive specialty steels. In one point of time, they want to replace the entire bearings. We proposed a solution to this material so that we can inbuild the core hardness of this bearing. You can see this is the size of the ball. You may see the flat face because it is a small uh, slice has been cut and it is being studied for the hardness. When we do a conventional process in the hardening in the surface, we can achieve the hardness of 60 HRC. You all know it's a bulk hardness, so HRC is Rockwell. In the periphery of the left side and the right side, there is no problem in the surface. But as we move to the core zone, you have a sharp depletion of 45, 43 someplace in 44. So the red one is the actual conventional process in which the bearing is treated. Actually, we have the problem, the hardness, the core becomes very soft. So the current design engineers demanded from us to deliver a core which has a minimum of 55 HRC. So we in the center we need to achieve this particular one. So we developed a technology in overcoming the drawbacks of the prior existing ones. So the prior one, before one, you can see the spheroids, which is our more complex ferrite ones. The current one, after the heat treatment is being modified, we get hard martensitic ones. So this conventional one is being withdrawn, and a very latest kind of heat treatment was proposed as a part of our patent. You can see, as I told in the top of the reactor, how does this LRP and SRP moves in fixing those subassembly. If you see the top view of this, you can understand how does this entire structure moves inside. We may understand this movement by in 1980s and 1990s born people. They understand in exhibitions they have a internal geared ones for making lots of designs in the papers. Similarly, you imagine instead of gears, we have a bearing structure in which this SRP will rotate on the peripherals of the LRP so that it can reach all possible positions in placing the subassemblies. So this was the description, and this was the treatment what we gave. It was the process what we followed is a double quench, double tempering. You can see 2 times it has been soaked. which is 820 degrees Celsius. It was soaked to 100 minutes. Then again it was quenched, first quenching. Then again it raised beyond this temperature, which was first was 900, second it was 1000 degrees Celsius. We call it as first arsonization and second arsonization. The second arsonization, previously when we have a waiting close, when we are soaking time of 100 minutes, this time we have 20 minutes soaking time, and suddenly we quench it, and finally the tempering process takes place for 2 hours. So we are around 13 to 15 trials we carried out to achieve this particular hardness, and these inventive steps made us to have a patent in that. What could be the applications of patent other than nuclear reactors? Yes, it has got potential applications in crane hooks, in mining equipments, especially in wind energy. Because wind energy, you design a power plant for 25 years, in which first 12 years we cannot get even single rupee in the payback on the return of investment. After 12th or 13th year only, it start paying back because the investment involved in it is very, very huge. So each of these, though we have worked for bringing the core hardness of a ball bearing in a particular reactor condition, it is going to give vital applications in the fields of cranes, which is in material handling, which is a mining equipments, excavations, or in the wind energies. So this was a data which is about how does this patent being. So as you can understand, the research doesn't end with publishing papers. It goes to the patenting. The moment it gets into the patent, all we speak about is the world share in dollars, how much China is now. You understand the significance of making research and development studies. It involves these much dollars of US, and the world share of the China in terms of patenting, and the amount of economical impact is 23 percentage. That they are the major contributors in terms of patent holding. And Japan comes to the next 13 percentage. German is followed by Italy and France. You can see the total exporters of ball bearings and amount of patents held by it. So now we have a second case study which I have personally involved in the evaluation of tribological properties of fluororubbers used in ISI wheel lining of PFBR. ISI wheel is nothing but in-service inspection robotic device. In that, the robotic device moves in using a fluoroelastomer wheels. So that rubber wheel is nothing but made up of fluoroelastomers, which is based on silicon rubber. This is how I segregate this small case study, which has PFBR ISI vehicle Disha. Disha in Hindi, you may know it is direction. They say they have an acronym of this particular ones. Fluoroelastomers come under the category of FKM rubbers, which is used as the robotic vehicles wheel lining material. So I have carried out pin on disc tribology test. Then I carried out Fourier transform infrared spectroscopic results to study what amount of bonds are really helping for the chemical inert nuts. How does it survive? How does it have a benefiting coefficient of frictions? Here in tires, we call it as traction coefficient. Then how does the thermal integrity by the thermogravimetric studies, differential calorimetric scanning calorimetry, study the TG, which is a ductile brittle transmission, and small conclusion for this ones. As you understand what is ISI, there is two vessels in the reactor. In order to understand what is ISI, there are two vessels, as it is having the reactors having an outer vessel and the inner vessel. The outer vessel is normally called a safety vessel. The red one is the inner pressure vessel. We need to traverse in this particular annulus gap by the robotic vehicle. You can see the enlarged vision from here. When you enlarge, you see these two. Here you have inner vessel and outer vessel. Inside the robotic vehicle crawls. Whereas when you enlarge from here to here, just have an expanded vision of this particular robotic ones. You see the wheels, which will enable to crawl inside the annulus gap. This robotic vehicle has a specific mechanism to study the joints of this surface. K joint, J joint, weld joints. All weld joints are studied by this robotic inspection vehicle. In that, it has a probe of RT-UT, also ultrasonic sensors. You may all understand just in ultrasonic, it will not work without couplant. Those who have gone for a scan for their kidney stone, or those who have gone for a scan for their pregnancy, we might have witnessed before putting the probe of ultrasound scanning device, they apply a gel, a cool transparent gel on your stomach or abdomen, depending upon the place of diagnosis. They just rub the probe on your abdomen, lower abdomen, because that couplant enables the sound energy to transfer very effectively from the surface to the internal organs. Similarly, in our robotic also, there is a condition. The couplant used in this one is called terminal. It almost looks like a transparent water-like one, but viscosity is much lesser than water. That terminal acts as a couplant for transfer of UT and RT waves, especially UT waves. RT doesn't require because radio waves doesn't have. So ultrasonic waves requires a strong medium for the stronger penetrations. So my work entirely concentrated on studying the coefficient of friction of this rubber material against the inner pressure vessel. When they gave two materials, they told both of them seem to be very prospective. They told the hardness. We all say hardness of bulk materials Rockwell. Sometimes when the bulk material is converted into micro samples, you make the micro hardnesses in Bernal, sometimes Vickers. In the most thinnest thin films, we call it as Knoop hardness, Knoop, Knoop hardness. But in rubber, the hardness is called a Shore hardness. Shore A is the scale, comes for 80 to 85 range. This FKM has black carbon filled reinforcement. In silica, you have brown silica filled material. You can see the metal bond product. You can see the polymer percentage varying from here to here and there. The carbon black used for reinforced is around 26.5 percentage. In silica, it is 27 percentage. The travel speed of the robotic wheel. This is given by the robotic division of Reactor Design Text Group (RDTG), which is in the ranging of 1 to 4 meter per minute. Operating temperature, you can see 185 to 200 degrees Celsius. Though 185 to 200 is very less compared to the metal exposed into higher temperatures, for the polymers, even this zone is considered as high temperature. The chemical structure of FKM is like this. The carbon bond is here and there. It has lots of fluorine bands covering. This fluorine carbon bond creates chemical inertness as well as heat resistance. This bond is very strong. The bond retains even in the higher temperature. The bond will never have any disintegration or any yielding for the temperature. This is called normally polymers we say cross linking, like that. One particular mechanism enhances the strength of this silicon based polymers. So just I wanted to have, because finding hardness using Rockwell, Bernal, we are all aware. Rubber hardness we are not aware. So I just wanted to have, this is the instrument what we use for finding the hardness of a rubber. The main mechanism here is the needle. When you expand or you just enlarge the needle, this is the mechanism. It is almost like a pricking glucometer. Like we just one needle comes inside, pierces and goes back. So that is giving the proportional value of the hardness. If this needle goes much deeper, assume or you can understand the rubber is of very soft nature. If the rubber is very hard, the amount of needle traveling will be very lesser. So that is controlled by the spring. So this Bryce German make rubber hardness tester. I just wanted to show how does the hardness testing happens in the rubber. And when I come to study the existing density, I come to know carbon was having marginally, it was like, see, both have 1.9. When you just concentrate the second decimal, you have slight variations. Silicon seem to have slightly more dense, and the matting material is actually 304L. Since the inner vessel and the outer vessel, we have one is 304, other one is 316. Hardness difference is slightly, you can see around, I cannot say 10 percentage, it was like 78 percentage difference of hardness. 76 Shore was carbon, silicon was having 81, and the hardness of 316 304L was 160 or 159. This is the experimental setup what we have for any kind of tribological pin on disc. Though they can replace pin by balls, in my condition, I cut extruded a rubber pin and the disc was rotated. You can understand studying there are transducer to calculate the wear encountered, there is one positional transducer to find the z direction VN, one more frictional force sensor which will also sense the frictional force. Once you find the frictional force, we all know mu equal to F by N. We know the normal force, obviously. Then we calculate the coefficient of friction, which is getting. Then this is the wear results we get comparatively placed. Carbon based fluoroelastomer showed very less amount of wear. You can see just following zero and very, very minimal wear. Whereas silicon, due to the marginal higher hardness, it was showing a better, more pronounced wears. Coefficient of reaction also were correlating with the wear results. Silicon was having presented with more coefficient of friction, carbon marginally lesser coefficient of friction. All the results were in same kind of representation where carbon used to have lesser wear resistance, and when this gives you the consolidated coefficient of frictional results. In that also we have a better coefficient of resistance is shown in carbon. You can see the weight loss comparisons in which all the experiments show carbon reinforced fluoroelastomers have very less amount of wear compared to the silicon based. The next set of experiments. Then comes the FTIR results where you have wave numbers. Every wave number and guides has its own significance. Though they come from the same family of materials, fluoroelastomers, there is only a shift, slight shift between the two materials. This Fourier transform infrared spectroscopy make us to understand which bond, which fluorine bonds, which oxide bonds are really crossing uh, with the transmittance. Amount of light is being transmitted. The spectroscopic result gives a significance of certain bonds, which is playing a vital role in giving the high temperature resistance to that polymer. Then comes, you can see thermogravimetric results in which the higher temperature in 400, which temperature you have the highest amount of mass loss. So you may understand when the temperature is gradually ramping up, one point of time the weight will gain, and one particular point the weight will sharply get losing. In that transition temperature, we call it as ductile to brittle. They say TG, which is glass transition temperature. TG is glass transition temperature. So comparatively, when you see the previous one and the other one, just two degrees only it was varying. This is actually when you plot it alone, you can see the gap. It has got two slopes in the differential scanning calorimetry. This had only one slope. We want to conclude the PO results of the fluoroelastomers. It has like the carbon reinforced has hardens, it wears more faster, it defies logic, but it can take heavier loads and effectively than silicon reinforced, which exhibits substantially more smearing. The tough silicon coefficient of friction range is 0.25 to 1.5, which is marginally higher compared to carbon. Though coefficient of friction is more, carbon is preferred than silicon reinforcement. The wear volume increases along with the load. The carbon reinforced at 200-degree wear in terms of weight loss is lesser compared to silicon reinforced. The dry sliding wear results of both were in good regard with FTIR, Fourier transform infrared spectroscopy, the thermal gravimetric analysis, differential scanning calorimetry results. So these are all the comparative correlated results. Now I just want to show some need of the our thing for our mechanical engineering faculties or core subject departments, mechatronics or production engineering, metallurgy. As we face as I started my career as an engineering teacher. First, after my postgraduate, I worked in an engineering college for 3 years time as a lecturer in a mechanical department. Then I upgraded myself to a regular PhD scholar in nearby NIT National Institute of Technology. I spent around 6 to 7 years in Trichy. I was like handling subjects to different mechanical people, production departments, some few labs for metallurgy. I used to handle certain on mm, some request basis on some leave time vacancies, like those kind of. I had a passion of our core departments, but current times we are facing crisis even in the high elite institutions. Admissions in mechanical metallurgy production is falling a sharp decline. So what could be our side contribution to create awareness and interest among the student fraternity? I just wanted to have few slides in this perspective. So one such association which is very very rich in terms of funding, very very rich in terms of conducting conferences, those who come from Chennai zone engineering colleges, you should make note of it. ASM, American Society of Materials, they regularly conduct conferences in Chennai Trade Center, which is there in Nungambakkam. For students, they charge very, very minimal charge, or I don't know whether they have waived the membership fee. You can get exposed to different companies ranging from coating companies, fabrication companies, metallurgically solution providers, R&D companies, microscope companies. Once you visit the stalls of the conference period, you can get lots of visiting cards, lots of contacts, not just from the suppliers. If you can establish a proper communication from the companies, those who are hosting the stalls, those who are put their stalls in the ASM sponsored conferences in Nungambakam or any other of the South India and the entire India, you can get into the level of finding internships for your students. So that kind of it's an international level body affiliated for the Americans, American Society of Materials. You should encourage yourself to get into such memberships. Then comes our Indian Institute of Metals. They also recently waived off the student chapter subscription money. There are two chapters near to Kalpakkam. There is IIM Kalpakkam chapter, SSN College, few of the college like Arupadai Vide Institute, Dhanalakshmi Srinivasan, Asan Engineering College. These are all the colleges under our IIM Kalpakkam chapter. Pondicherry is again with our IIM chapter. We continuously year after year we conduct Brahm Prakash Memorial Quiz for 11th and 12th standards to create awareness about metallurgy, mechanical core subjects. For Chennai-based colleges, they have IIT as IIM Chennai chapter. IIT Madras has. Every single state in IIT in Hyderabad, IIM Hyderabad is there is a chapter. IIM Bhopal, IIM Odisha, Bhubaneswar, IIM Thiruvananthapuram. In IIM Salem, there is one chapter. Coimbatore, there is one chapter. So only the colleges around them, especially the mechanical engineer students, should contact with this chapter bodies and enroll themselves, get members, and they conduct symposiums, they conduct seminars yearly. In the month of November, they conduct a National Metallurgical Day celebration. In that day celebration, they keep ATM, annual technical meet. It's very very useful for undergraduate students. Again, group of companies will come, they will put their stalls, you can collect their visiting cards. Once you go to the stalls, they will describe about their product capabilities, their job opportunities. If you explore, you can try talking with them again and again, what is their real skill set needed for their firms. Especially Chennai Metco in our Chennai zone, they keep on recruiting BE material science graduate from Anna University. Why they say that is, every single conference they will put a stall or a conference. Like 3 4 companies in Chennai itself, they have come for offering not just industries. Few of the research scholars are also going and taking the help of mechanical characterization. Those who are doing experimental works like micro labs. Then there is one TII testing company. They don't have SEM, but micro lab they have a SEM facility. In Satyabama, they take SRM on payment basis. They take the scanning electron microscopic images, EBST, EDS, those kind of facilities being offered over the payment. You have to book the slots. Then comes Indian Institute of Welding. This is also one very important chapter where production engineers, mechanical engineers, they can keep about following about what is the national welding seminar happening, where does it happen, what are the companies like FLD Smith, Malem Electrodes, then Adar Pontec, a lot of companies are Fronius. Then there is one company, ESAB. These are all the leading welding electrode companies. The moment you become association, affiliation, chapter members, you come to know about the real core job opportunities by getting exposed to those companies. This is one beautiful chapter. If you personally want the contact details of ISHRE, Indian Society of Heating, Refrigeration, Air Conditioning, Chennai chapter, here the president is my very close friend. He keeps lots of programs for students, especially hackathons. Hackathons, they are the, because these are all the buzzwords which we lack actually. All computer science, IT, you may see every departments now like they have merged into kind of cyber security, lot of CSBS, computer systems and business systems, then gaming technology, IoT, artificial intelligence, data science. Several bifurcations have come in the department of computer science. But our own core department, which we require mechanical engineers to work, ISHRAE, I find only very few institutes have this affiliation or these clubs. Our core department should also promote such club activities, which will make the student this learning process a more interesting, as well as you can get some assured placements from companies like Carrier, Hitachi, Blue Star. They have their hackathons, and once you crack the hackathons, automatically you get placed with some 3 to 5 or 5 to 7, depending upon the company and the requirements. I mean to say the cost to company, CTC, LPS. Then this is one automotive. This I think a few of the colleges have already been enrolled with the Society of Automotive India. They have conduct regular automotive fairs and conferences. This makes you to have hands-on touch with presenting your papers related to the automobile. Now we are just gradually in the transition period of hybrid vehicles. Already electrical vehicles have started, and we all, as a mechanical enthusiast, people feel that electrical vehicle is not a viable solution in long run due to the amount of the weight in which the battery contributes. So the future could be either hybrid or it could be hydrogen based powered cars. This is, we have to wait and see. These are all the various fields. Now currently government has launched E20 petrol, where 20 percentage of ethanol. Now we are going to have some relevant vibrational or wear related. It could be, we may not know what is the real time implication of going 20 percentage ethanol addition. Though they say it is safe, some amount of component wear and tear because of the calorific mismatch of ethanol and petrol. There is going to be a potential research gap for the upcoming, because earlier research gap was only meant for PhD students. Now I find uh, beautiful works coming from undergraduate students publishing in reputed SIE, Scopus, and all index journals. All UG students have started publishing. Only thing is you need a proper mentor, proper time planning, proper experimentation, proper report making, proper result discussions, and you need to find a journal to sell your idea. So that is why people repeatedly say you enroll yourself in different affiliations, clubs, to enrich your knowledge, to get exposed to the current research trends. This is one more ISNT for non-destructive testing. This RT, UT. I feel like a lot of diploma mechanical people, they study this level 1, level 2 of non-destructive testing. They get into the field of quality control, quality assurance. Then there is some examinations like Six Sigma, TQM, Pocoyo, 5S. These kind of certifications, you should acquire it in certifying bodies like NPTEL, Udemy, Upgrad. These are all the different bodies which is existing in the current scenario. We should not rely on certain AI engines like Gemini AI, ChatGPT. It can be always taken as a standby, but you should not rely totally on it. Instead, you should rely on building your skills by enrolling in uh, sites like, as I said, Udemy, Upgrad, Coursera, these kind of sites you should understand, and you should start learning new skills, especially NPTEL. NPTEL is one good platform. This is one upcoming last 10 to 15 years it is alive. For this is a multi-dimensional people coming in this. Society of failure analysis, more people are from civil engineering. Few are next to that, more people come from metallurgy and then mechanical engineers. So any failure related study is now three departments: civil, mechanical, and metallurgist. All these three people play a role in this association. So these are all the other funding organizations where proposals can be pitched in for getting a 2-day program. You can ask some partial funding for conducting a faculty development or outreach program to the society to create awareness about new and renewable energy. Say when you want to have creating a prototype of a windmill or solar harvesting, harvesting in the sense throughout the day the sun direction keeps on changing. You create a automated gear mechanism so that along with the sun's location, the the parabolic collector also moves accordingly, so that it harvests the maximum performance in moving and tracking the sun. Same with the wind energy. We can create about how to have artificial tunneling effects between buildings, and there are some various mechanisms in which even the tunnels what we go use for our roads, for vehicles passing through the mountains or some train tunnels, due to the vehicles movement, how can we install sideways to have a minimized power producing windmills. Those kind of projects can always be pitched. Then MSME schemes, SARB, CSARs. So apart from that, if I could have touched some of the other than just last 10 slides, I intentionally want to have a non-technical view because I basically see some of the colleges either they have reduced the amount of seats from double intake to single intake. Few colleges I see very lesser amount of seats. I did not personally have a good feel about reducing getting means seats getting reduced, and that will have implication when the need comes. Think about another few years, a lot of private players is going to come in the field of nuclear reactors like Jindal, Larsen Tubro. They have right now they have already started nuclear divisions. L&T has started nuclear divisions, and they are eyeing SMRs, small modular reactors. So in the near future, every single industry or company they can have their own modular reactor. Once you load the fuel, the power crisis for the next 10 to 15 years is solved. Once you load the fuel, the uranium loaded inside the small modular reactor is going to come for a period of 10 to 15, say 13 to 14 years. There is no looking back on. You get a seamless power supply through those SMRs. So definitely, we are going to witness those SMR in industrial scenario in the coming next 5 years. During that time, though chemical engineers are already sparse, the only persons who can work on seeing the drawings, fabricating, executing, erecting, and servicing, producing, production on the floor, it could be only mechanical engineers. There could be a severe shortage of this particular field. Current day, we are all eccentric, little skewed or little biased towards all software circuitry related departments. But after a few years, it is going to be, as our IIT Vice Chancellor has rightly quoted, there is going to be huge scope for the core department graduates. So if you find this particular talk is has tried to give some insights about the advancements in the materials in terms of strategic importance, metallurgical importance, economical importance, kindly send your feedback. And if you want further any clarifications or any information about, it could be on you are taking the research to the next level, collaborating with other departments, facilities available, and then suppliers of some materials, where you can get these materials, how do you assure, how can you get a test certificate, how can we assure whether the material what we get is of right quality, right composition. Those things, if you feel, if you want, if you feel, you can always take my help by mailing to me. Thanks for your patience in listening this talk, little longer talk, 1.5 hour. You have been very patient in listening. Now, if you want to discuss something, we can always have a question session.
Advance, I posted some of the questions, sir. Are there promising advanced materials such as oxide depression, strengthening alloys, or ceramics composites being considered for tribological application in future nuclear reactors? Hello,
Go ahead, sir. Go ahead.
sir. This is a question asked by one of the participants. There are
Yeah,
promising advanced materials such as oxide dispersion, strengthened alloys, or ceramic composites being considered for tribological application in future nuclear reactors.
that's a very good question. ODS, he's asking about oxide dispersed strengthened steel, ODS steels. That too, ODS based composites. Currently, the research on this particular perspective is taken up by, as of now, in national importance, in BRC Bombay, they are working. In Kalpakkam, we are not having ODS based composites for wear related studies. Chinese people have already taken this ODS based wear resistance works. This is actually a potential area where we can definitely start. Only thing is, you should have a facility to make those composites in our laboratory facility. Certainly, the material what you are proposing, ODS based composites, are going to have a bright future in the coming days, as we are going to have different kind of reactor conditions. Definitely, we will have potential application. That is the right area in which you can always concentrate. Anybody else?
So next question is what experimental techniques commonly used to simulate and study the tribological behavior of nuclear reactors in laboratories?
Yes. So as of now, we have through 2 to 3 tribometers in our laboratory. One is a uh, air machine. We call it as in ambient conditions. We test pin on disk. The other one is a vacuum condition, which will simulate the sodium atmospheres. Apart from that, we collaborate with IIT Madras. They have a RTech VR simulator in which you can go to the level of simulating fretting wear. So all tribometers generally mimic the mating parts. Whenever a material is being asked what is the wear resistance, you should ask an opposite question to the person who is asking what is wear resistance, because the opposite person has to understand against which material. Any material's wear resistance cannot be quantified as such. Since wear or tribology is a relative phenomenon, so all those pairs and designs decide what mechanisms and design orientation we are using. It could be pin on disk, it could be ball on disk, it could be flat on flat, it could be roll on block on disk. So the current conditions what we have tribometers in our perspective is we have in thin film sectors they have a high temperature tribometer. It can go up to 500 degrees Celsius. In our department we have a low temperature tribometer. For certain fretting wear applications, we are taking help from the facility we are now going to developing. It is under the intending stage, but currently we rely on IIT Madras for doing the fretting wear. So compared to the sliding wear, fretting is like it's involving vibratory frequencies. It's reciprocating, but with lesser amplitude, with higher frequencies. So these kind of wear, especially when you call the vibrating steam turbine, steam generators with the support structures, then your fretting wear study becomes very important. When your subassembly is moving with the grid plates, then your sliding wear study becomes important. So depending upon your wear conditions exposed in the reactors, your study gets its significance. So this is what we use. Apart from that, some kind of simulations with abacus is also parallelly happening in our department. It's a very good question in which you can take up those tribological related research works. Currently, we have a few companies in our Bangalore, Chennai. They supply tribometers. They keep on having high temperature facilities also, with not just catering our nuclear reactors. To major extent, it caters the automobile sector, especially brakes, clutches. So if you want to characterize the frictional coefficient, automatically you have to look up on certain matting materials in automotive perspective also. This is also a very good question. So anything else which I can say?
So next
In
question
that
is
case, yeah, please go ahead. Go ahead. What are
what
the?
are the major tribological challenges faced by structural materials such as
Yes.
stainless steel and nickel alloys under nuclear reactor operating?
Okay, I will put it in a generic form. The major challenges faced by any of the tribological atmosphere, especially stainless steels or nickel, is high temperature. Then, the moment high temperature comes to the image, the next chemical degradation is oxidation. So, due to the higher temperatures and non-uniform loads, along with this oxidation, when you have an oxide layer which is being uh, initiated, few oxide layers they really act as a glazed layer and act as a lubricant. But few oxide layers which gets detached, delaminated, when it is getting caught between the two mating materials, that flaked off and delaminated oxide layers will act as a third body abrasion. So, when you study the mechanisms of tribology, you say about single body. There is one two body wear mechanism. When two bodies have, when there is a third particle entrapped, a hard debris between the two bodies, so the mechanism becomes three body abrasion. So these high temperature atmospheres is becoming responsible for creating those oxides, and few of the oxides which is selectively delaminating gets entrapped between the moving particles, and this becomes the basic one. And there are one more challenge in, I want to say, in nuclear reactor. We don't have the luxury of using lubricants as in the automobile sectors. We can use lubricants. In nuclear sectors, the use of lubricants is totally ruled out, just because of the clumsiness and just because of the half life of the radioactivity. All those reactive reactor conditions ruled out the possibilities, especially in the core zones inside the reactor. Any use of lubricants is totally ruled out. So you need to have a trade-off between harder surface. You need to go by choosing sometime a better enhanced material. In some time, if you cannot choose, like in take up an example of inconel, which is used at support structure. What they do is the inconel is subjected to aluminizing, pack aluminizing process, in which it is being heated in a mixture of aluminum chloride and alumina, so that the aluminum gets into the superalloy surface, makes an intermetallic, comes out and deposits in the layer. The process is called aluminizing. The external, the few microns of thickness which is deposited on the superalloy has the required hardness. Automatically, the wear resistance is achieved for the superalloy support structures. So in some cases you go for a better material, in some cases you go for the surface modifications. Depending upon the affordability and real-time experimental applications, real-time industrial situations, either to replace or to go with some modifications, they adapt the solution accordingly. This is also one question which may be taking you for a further perspective of research. What are all the vulnerable conditions, temperature conditions, what are the load conditions? Then we gradually, with lubricant, without lubricant, how can you segregate and how can you single out which is the best one, which is not the suitable one. Here in our reactor conditions, the usage of lubricant is totally ruled out. Thank you. Then any other questions are there?
Yeah, sir. One more question is there, sir.
Yeah.
How can tribological research contribute to extending the life of nuclear reactor components and enriching safety and reliability?
Yes. Actually, whenever you design a reactor, it is meant for a design period of 30 to 35 years. Every product has one particular allowance given during the design time itself. What is the wear tolerance which can be given? The moment you go on investing time and money and research team in enhancing the wear resistance of the material, you not just ensure the functionality of the product by contributing a very good wear resistant material to the moving mating parts, you ensure the prescribed design life of the reactors. Unprecedented losses, unprecedented failures due to a failure of a turbine, due to the failure of a moving reciprocating pump can be avoided if you have chosen the proper material which has the required wear resistance. So sometimes we encounter certain unprecedented, unexpected, premature failures. We immediately visit the place, we immediately take the material, we replace it with some other alternate arrangement standby, and we analyze the failure modes. What is the cause of sudden wear? What is the mode of failure? So we, before going for the design of materials, when you plan a particular act of processing, when you choose the materials, we should thorough survey of the existing literature of the reactors throughout the global conditions, which is the proven material. There are certain codes which has a strict yardsticks. The codes, what we call it as, gradually now we have our own BIS is making material codes, Bureau of Indian Standards. Previously it was ISI, now full material standards are coming from BIS. We rely on two codes for one French code, one is RCCMR, other one for materials we have ASME codes. As per the codes says, the codes are they follow very religiously. It is the Bible for any other design engineer, the ASME codes and RCCMR codes. What is the allowed thickness, which material, in the material, what is the allowed chromium percentage? So those compositions has to be very strictly followed. Once you follow and you ensure the corrosion resistance, wear resistance of the material of a particular component, the functionality of the reactor is ensured. The reliability is very well proven, or very well we can have the confidence of the particular life period, or say about 30 years. If this is the design life of the reactor, by having a proper wear resistant material, we can ensure the design life. After now we may understand maps after the time is over, we never go for sudden decommissioning. They again do the life extension by modifying, and they try to run the plant as much as possible. Again, there is not on the whims and fancies of the R&D people. There will be a totally a different third party evaluation and inspection. There is a department called Safety Regulatory Inspection, SRI, maintained by the upper body called Atomic Energy Regulatory Board, AERB. So AERB and SRI, they together come to the places of life evaluation, quality of the particular components. They keep on do periodical inspection. They are the typically third party inspection party. We ourselves in our IGCAR, we have our own QAD, NDED for our inspection. But whether those things are being followed and properly adhered, that is taken care, and they have to certify. AERB has to certify. They work with white and black, no gray zones in AERB. If there is slightest of the slightest violation, they never have any mercy in approving any of the violations. They simply mark it as non-conformity, and once it is being fixed, again they go for a thorough scrutiny to give a permission to carry out the next level of activities. So once you have to ensure certain amount of wear resistant property to the component, that has to be adhered. That is why I say it is to be religiously followed. There is no second thought, no dilution of any of the yardsticks, especially when it comes to the dimensions, strength, corrosion resistance, and wear resistance. Thank you.
Thank you, sir. I hope
Thank you.
everyone will get their
Yeah, you
answer.
have any doubts or anything, you can always send me the mail. I'm very eager to have interactions. Let me get the list of participants through the organizers. I would like to see which are all the colleges actively participated in this particular one. I would like to interact with them in future also. So in this regard, I just want to again thank the organizers for finding me as a person, resource person, to share my insights about the reactors, the materials associated with nuclear reactors, wear-related case studies. So I would like to thank
Hello, sir. Sir, we can't able to hear your voice, sir. Hello, hello, sir. We can't able. Sir, I think you are in mute, sir. Sir, I think in your mute.
yeah, no, yeah. Suddenly it got disconnected accidentally. So I
Okay.
thank once again the organizers for giving me an opportunity to deliver this elaborate lecture to our faculty, people associated with mechanical engineering and other departments also. I personally thank the organizing team for giving me this opportunity. Thank you. Thank you for your patience in the late evening hours. Thank you for your patience. Thank you once again.
Thank you, sir. So, on behalf of the organizers and all the participants, I will take this opportunity to sincerely thank you for thank our esteemed resource person, Dr. N.L. Parthasarathi sir, for delivering a such insightful and engaging session today in the field of nuclear reactors and our material selections. So surely your expertise and valuable inputs and practical perspective have enriched our understanding and made this session really truthful, sir. Really, we are grateful for your time, effort, and dedication to make this session knowledgeful. Once again, I'm thanking you, sir.
A pleasure is mine, sir. Pleasure is mine.
Sure, sir. As per your request, I will share all the details to you, sir. Surely, the peoples from our side they will contact you in future, sir.
Thank you. Thank you.